Refrigeration or air conditioning system works by absorbing heat from interior air, transferring that heat to outside air, and rejecting it there. Heat flows from hot to cold, and there must be a temperature difference for any heat transfer to take place. The absorption of heat occurs in the evaporator coil, where the low pressure and low temperature refrigerant absorbs it. The rejection of heat occurs in the condenser coil, where the high pressure and high temperature refrigerant rejects it. Shown here is an illustration of a basic refrigeration system. The components of this system are the compressor, discharge line, condenser, receiver, liquid line, metering device, evaporator, and suction line. Roll the cursor over each component to see the basic function of each. To learn more, select from the menu on the left. The compressor serves four functions. Along with the metering device, the compressor separates the high and low sides of a system. It acts as a refrigerant pump and circulates the refrigerant through the system. It raises the temperature of the refrigerant by compressing it to a higher pressure, and it compresses the refrigerant vapors, tightly packing the molecules together. A pressure separation or difference in pressure is mandatory for refrigerant flow in a system. Without the compressor as a refrigerant pump, refrigerant could not reach other system components to perform its heat transfer functions. A compressor raises the temperature of the refrigerant vapor above the ambient temperature by raising its pressure. Raising the refrigerant temperature above the ambient temperature allows for the flow of heat from the refrigerant to the ambient. The refrigerant contains heat absorbed in the evaporator and suction line, and any heat of compression and motor winding heat generated by the compressor. The compression of refrigerant vapors is actually preparing the vapors for condensation, as it increases the density of the refrigerant gas molecules. More tightly packed refrigerant molecules make for easier condensation. The discharge line carries the high-pressure vapor from the compressor discharge valve to the entrance of the condenser. Some heat rejection to the ambient occurs in the discharge line, cooling the refrigerant slightly before it reaches the condenser. The beginning of the discharge line is the hottest part of the refrigeration system. On hot days when the system is under a high load and may have a dirty condenser, the discharge line can reach over 400 degrees Fahrenheit. The first passes of the condenser coil reject heat from the high-temperature refrigerant vapor. Once the refrigerant rejects enough heat, it will reach its condensing temperature and condensation, or the phase change from gas to liquid, can begin. As more heat is rejected from the 100% vapor, it will force the vapor to gradually change to liquid until 100% liquid is all that remains. Condensing is system dependent and usually takes place in the lower two-thirds of the condenser. Once the refrigerant is 100% liquid, further rejection of heat starts to lower the liquid temperature to the evaporator temperature. This is an important process because it will reduce flash loss in the evaporator, so more of the vaporization of the liquid in the evaporator can be used for useful refrigeration or air conditioning. The receiver acts as a surge tank. Once the liquid refrigerant exits the condenser, the receiver receives and stores the liquid. The liquid level in the receiver varies depending on whether the metering device is throttling opened or closed. Receivers are usually used on systems in which a thermostatic expansion valve is used as the metering device. The liquid refrigerant in the receiver may lose or gain heat depending on the surrounding temperature. If the refrigerant is warmer than the ambient, the liquid will reject heat. If the refrigerant is cooler than the ambient, heat will be absorbed. To prevent refrigerant from sitting in the receiver and heating up, a receiver bypass is often used to bypass liquid around the receiver. A thermostat with a sensing bulb on the condenser outlet controls a bypass solenoid valve which routes the refrigerant directly to the liquid line and filter dryer if it's at a predetermined temperature. The liquid line transports the high-pressure liquid refrigerant to the metering device. In transport, the liquid may either lose or gain heat depending on the surrounding temperature. Liquid suction line heat exchangers, in which liquid lines are wrapped around suction lines to help them reject more heat, can be installed in existing systems. The metering device is a restriction that separates the high-pressure side from the low-pressure side in a refrigeration system and meters or regulates the flow of liquid refrigerant from the liquid line to the evaporator. The compressor and the metering device are the two components that separate pressures in a refrigeration system. The restriction in the metering device causes liquid refrigerant to flash to a lower temperature in the evaporator because of the lower pressure and temperature in the evaporator. There are several different styles and kinds of metering devices on the market with different functions. These are discussed in the section on metering devices. The evaporator, like the condenser, acts as a heat exchanger. The pressure drop through the metering device causes vaporization of some of the refrigerant and produces a lower temperature in the evaporator. Heat from the ambient air around the evaporator coils is absorbed by the lower temperature liquid refrigerant. As heat is absorbed, the liquid heats up to its evaporation point, then changes state from a liquid to a vapor. This is much like adding heat to a pot of water until it boils, changing state from water to water vapor. The last passes of the evaporator coil allow for more heat to be absorbed by the refrigerant, ensuring that it is 100% vapor and that no liquid remains. The suction line transports low-pressure heated vapor from the evaporator to the compressor. More heat is absorbed by the refrigerant in the suction line, which decreases the density of the refrigerant vapor. This helps ensure that the compressor will see vapor only under low loading conditions and prevents compressor overload. It also protects the compressor from any liquid slopover, which may result in valve damage or diluted oil in the crankcase. There may be other components in the suction line, such as liquid suction line heat exchangers, suction accumulators, crankcase pressure regulators, P-traps, filters, or screens.